I'd like to spend a little bit of time talking about conversion or fractional conversion. It's a term that is really useful for chemical reaction engineering. Um, so let me try to approach it in a few different ways. First, a definition. So when you're thinking about conversion, you should be focusing on your limiting reactant. And if we imagine a situation where you have example, some kind of species A, then what conversion is so conversion, I'm giving it a subscript A, but there's really just one conversion for the reaction. It would be moles of A reacted over the amount over the moles of A fed or supplied. So this, is going to become more important, especially in the context of reactors that involve flows in and out. From a batch perspective, well, it's relatively easy to know how many moles you've started the reactor with, and then it just kind of sits there. But if you're thinking about a continuous system, you want to be thinking about how many moles of A you're feeding and how many reacted. So let's just work with this sort of more grammatical sort of definition and convert it into something more mathematical. If we think about how many moles of A we fed, just to think about the denominator first, as it's easier, that we use N to represent moles, and it's Na naught. Then what we want to figure out is, how many moles of A reacted. And if you're wondering, partly I just want you to feel comfortable with being able to do this intuitively, although it may be the case that, especially if you're taking an open book exam, you don't quite have to memorize this, but you should, learn and understand it, right? So how do you figure out how many moles of A reacted? Well, we have this other term, Na. But Na is how much we have at any given time. It's not how much got reacted. So how much we started with minus how much we have left is how much was reacted. And so that's where you get this definition then mathematically for conversion. Okay, so if we go ahead and we can rewrite this in a few different ways, and I just want to do that so that you understand where the book is doing some of its transformations from. So we can rewrite this like so. I guess I'll leave it for there now and just try to go into a more concrete example. So let's talk about a CSTR. And let's focus on a specific example that the book might have. So CSTR design equation. What I'm trying to explain in this video is why there are so many transformations in chapter 3. So many cases where you see a design equation rearranged. So my goal is to be able to explain that hopefully in some effective way in this video. So we have a design equation. I think this is equation 3-16, where for a CSTR we have the volume is equal to the molar flow rate of species I coming in minus the molar flow rate of species I going out, and over the negative rate of formation of species I. Okay. In equation 3-17, we have this rearranged. So we have the volume of the reactor over the molar flow rate. In this case, I'll just use A. I'll substitute that in as our limiting reactant. And so we have volume over flow rate of A. there's been some rearrangement over here to make that happen, using just the definition of conversion. So if you want to better study and understand what was done to go from here to here, take note of the conversion definition that I provided on the previous page and see if you can do that substitution for molar flow rates. Every case in which I used an N can be replaced simply by an F. Conversion works the same way, whether it's molar flow rates or just moles. And so you should be able to get to this. Now the question might be, why would you want this? Why not just work with what you have here? And so there's at least two reasons that I can think of for why conversion is a valuable term. So the first has to do with the replacement of variables. We'll call this the sort of general replacement or substitution of variables, of species variables, specifically variables. So what conversion lets you do is basically you can use conversion to replace, for example, any kind of rate expression that might depend on the flow rate of A, or this could be the concentration of A, and say the flow rate of B if there's another reactant, or the concentration of B. Specifically, if you have rate expressions where imagine you have K times CA times CB. Okay, so here's a situation where you know you're going to have these two variables, but you know that they're also linked. The way that A is going to change is going to affect B. If B is reactant, it's going to fall in line in a way that a stoichiometric table can get at. And so we will soon use and set up stoichiometric tables to show you how then you can do this. The other reason why conversion is valuable is because conversion may be what you're given or seek. Okay, so what I think is an interesting example that helps explain what I mean here is that you don't always need to know your composition of your stream and exactly how many moles of A you're feeding in per time and how much you're feeding out. You might just, sorry, not feeding out, how many moles of A are coming out of the reactor. You might just be given a target where, hey, you want to design a reactor that's going to convert 90% of A. And you can solve for that. And we're going to look at exactly how to do that now for a CSTR. So let's go ahead and have this example problem. So we'll call this example 3. Example 3, CSTR reactor sizing. Okay, so let's say we have a CSTR. All right, we're going to say it's a first order reaction. We're going to say it's CSTR, so it's a steady state. If we didn't say that, you can assume that. You should state that assumption. We're going to have the reaction A goes to B at some rate K. We're going to be given a rate constant for K of 7.6 times 10 to the minus 3 inverse kiloseconds. And now we're also going to be told that we've got a volumetric flow rate in of 0.5 meters cubed per kilosecond. we're going to be told one other thing, that this reaction involves liquid phase. And our prompt is what reactor volume achieves 40% conversion of A. What reactor volume achieves 40% conversion of A? So let's think about this prompt and the setup for a moment. We've got a reaction, it's irreversible. We know how much material generally is coming in, and we don't necessarily know the molar flow rate of A to begin with, or how much is leaving, but we know that we could potentially adjust that the composition of our stream in, and still with a particular reactor volume achieve 40% conversion of A. That's our target, sort of regardless of what we're working with. And that's all the information that we actually need in order to solve this problem. So let me go ahead and start to write the solution here. So I'm working out this solution. In this case, I won't give you time in advance to work it out yourself. You can always pause the video if you'd like, unless you're watching live in class, then I guess you can't do that. But let's go ahead and get started here. So this isn't going to be too complicated if we start thinking about our rate expression as a place to start. Then we know that this is a first order irreversible reaction, so we have Ra equals minus KCA. Great. If we think about what parameters we were supplied with, we can take this 40% conversion and rewrite it as 0.4. So there are a couple of definitional things I left out of explicitly out of conversion. One of them is that the max conversion is 1, at least for an irreversible reaction. So percentages, 100% conversion is a conversion of 1. And I mean, if you look at the actual definition that I provided you, either mathematical or in words, you would see why that is. Something I should mention is that if your reaction were irreversible, if your reaction were reversible, so it could go either way, then your maximum conversion is not 1. For a reversible reaction, your maximum conversion is the equilibrium constant. So that's just something to keep in mind. Okay, that was a small sidebar. Let's continue. So what we're gonna have here is well, I'm gonna take the design equation that I wrote before. So this is the CSTR design equation, and I had shown you that you have the volume of the reactor over the molar flow rate of A equals the conversion of A over minus RA. And so maybe your first thought is, okay, I'm trying to solve for this. I don't know what this is. That could be a problem. And then you've got this information, and you can probably figure out this, except you don't know what CA is either. So maybe you're thinking, oh, well, you know, Professor Kunjapor's led us down a weird path here because, yes, we have conversion, but there's some things that we don't really know here. So bear with me. One of the things that you can do, and so this solution is partly meant to emphasize this, is that you can basically make a substitution where you introduce the volumetric flow rate. So remember that, well, maybe I'll erase this for a moment. I'll just say, recall that your molar flow rate of A coming in, or FA naught, is really just your volumetric flow rate coming in times CA naught, your concentration of A that you started with. And so I'm going to do this substitution, just to further rearrange these design equations and to just kind of show you how these kind of rearrangements can be helpful, or how you might need to be doing more rearrangements even when you use terms like conversion here. So this gives you VR divided by V naught times CA naught, and now you have conversion of A. And then if we do the substitution for RA, you've got KCA over here. All right, so now in this equation, now we have a few things that we know and still a few things that we don't. We found a way to introduce the volumetric flow rate. We don't know our starting concentration of A. We don't know our final concentration of A. We know also this isn't a differential equation, which makes sense. We're working with the CSTR. So we really just want to be able to algebraically make some substitutions to get things in terms of what we want. And this example will hopefully illustrate why conversion is a powerful concept, because we can substitute out our CA naught and CA. And so the following page will show you how to do that. So let's go ahead and just rewrite what we had, but I'm going to move my CA naught over to this side, to the right-hand side, over KCA. So what you can see is that we have a situation where what we want to do, I guess our goal is to substitute terms for CA naught over CA. And so let's go back to conversion. If we think about the definition of conversion, I mentioned before, you can change moles to molar flow rates. You can also change them to concentration. So remember, it's how much you fed. It's how much you reacted over how much you fed. I always start with the fed on the denominator and kind of work my way back. So that's our definition of conversion. If we do a little bit of algebra here, we can multiply both sides by CA naught. And then we can get CA isolated. I'm kind of switching sides here. And then we can get to CA naught over CA is 1 over 1 minus conversion of A. So I did skip a little step here in that I first divided both sides by CA naught, and then I had 1 minus conversion of A, and then I inverted that. So maybe if you just want to see that, just for the sake of completeness, I'll mention that what I did here was have CA over CA naught equals that. Great. Okay. So occasionally I'll do little things like that. Hopefully that won't throw you off too much. So now if we go back to here, what the implication is that essentially we'll say, I'll use a different color so that it won't get confused. We had CA naught over CA, and we know that it's 1 over 1 minus the conversion. So we can also move the volumetric flow rate to the other side, and what we have is volume equals volumetric flow rate over, let's take our rate constant K and keep that separate, and then we have this other term, this 1 over 1 minus conversion of A, and then we still have the conversion of A here, so we have it in the numerator too. And let's go ahead and plug in some numbers and do some real stoichiometry here and make sure all our units check out. So we started with 0.5 meters cubed. I'm going to draw a line. This is the way I like to do my stoichiometry from chemistry in high school. Okay, so 0.5 meters cubed per kilosecond. And then we've got a rate constant of 7.6 times 10 to the minus 3. and that was inverse kiloseconds. That looks good so far. I'll go ahead and cancel out units as I'm working through. Maybe you want to wait until the end, but guess what? There aren't actually any more units left because the conversion numbers are all dimensionless. So we had 1 minus 0.4 here, 0.4 I should say, and then we had 0.4 here. And so our units check out. We have units of volume. That's what we want. And when we do this, we get V equals 43.9 meters cubed. So look at that. We now know that if we want 40% conversion, and we have a flow rate coming in at this rate, and our rate constant is this, it doesn't really matter, you know, how much our concentration of A is in the inlet stream. Regardless, we need this volume, and that's because we're trying to hit a conversion target. So hopefully this exercise shows you a little bit of how both conversion can be useful. It hasn't yet involved the stoichiometric table component of it, which is probably its more common use, but I've been trying to keep things pretty simple in terms of the number of species involved so far. That's gonna change soon. Yeah, all right, we'll do one more example in the next video.